Hello, everybody. And so today we're going to be actually starting off our physical chemistry lectures talking about a topic that really isn't chemistry at all. We're going to be talking about light. Now, this may seem like an odd place to start, but light is one of the fundamental tools that we are going to be using to build up the whole rest of this semester. So, one of the big things to remember about light is that it's an electromagnetic wave. So this is going to come with a little bit of some oddities. First of all, it means that we're going to be treating this as a system of wave mechanics. So we're going to be brushing off all of our good old classical physics in order to describe light. Second is the fact that it's electromagnetic, which means it acts as both an electric field and a magnetic field. And so one way to think about this is it's kind of a moving field of charges. So it's going to have strong interactions with any charged particles. This is where light becomes really important to chemistry. Because in chemistry, we are more or less devoted to trying to understand the behavior of two fundamental types of particles. First, electrons, which are fast moving, negatively charged ions, which means that they will have quite a strong interaction with this electrical field. Because again, it's a moving negative charge, which will interact with a moving electrical field. Second, we have nucleons. So this is going to be mostly dominated by protons, who have, again, a positive charge. But due to their slower movement, they don't interact quite so strongly with this electric field. But under the right circumstances, you can indeed get some interaction with the electric field. But more often, we end up getting interactions with magnetic fields. So that's going to be a lot of the interaction with electromagnetic radiation from a nuclear perspective. And so at the end of the semester, we'll start dealing a little bit more with the magnetic field. But for now, we're going to really be focusing in on this electric field component of light. And this is a big deal for two major reasons. First of all, if I have an electron happily moving around an atom, I can actually use light to cause an excitation in that electron. I can move the electron. But the issue is, as we'll see later, due to quantization, I can't just willy-nilly move an electron with any type of light. Only specific types of light will cause very specific types of movement. So if I know what types of light are being absorbed, I can tell a lot about the behavior of my electrons. Similarly, if I have an electron that is already excited and high energy, it can go ahead and move down to a lower energy level, releasing energy. And any energy that's released is also going to be in the form of light. And this is going to be a big dominating feature of nuclear movement. Any change in the energy of an electron is very typically going to be related to releasing or gaining some of that energy in terms of electromagnetic spectra. In other words, we're going to see a lot of emission and absorption of light. And that's what we're really going to be looking at. However, in order to be able to really probe the behaviors of these atoms, I need to try and put some numbers to the system. So what we're going to be doing is relying on, again, this oscillating intensity to essentially make use of some of our wave mechanics that we've seen in physics. We're also going to take advantage of the fact that light generally moves in a straight line. It has very low sort of refraction, so typically I can treat it as a straight line movement, which is going to add a lot of practicality in that we can usually source our emission and absorptions very reliably. However, again, we need to try and put some good numbers to this movement or wave properties. And so what we're going to be doing is adopting two of probably your old favorite ways to talk about about waves, wavelength and frequency, and we're going to be adding in a new one that's mostly used by chemists these days, and wave numbers. And what these are going to be doing is a way to essentially quantify our description of light. And we're going to be doing this mostly in kind of relevance to essentially the maximum or peak intensity of the light. So one way to kind of think about this is, again, in terms of ocean waves. You can monitor the movement of the waves just by looking at the peak of uh, the peak of the wave, because this is the one that's going to have the part of the wave that has the strongest interaction. It doesn't mean that the other parts aren't part of the wave. It's just that this is often the one that's easiest to see because it's the one most likely to move things. Just like an ocean wave is most likely to, say, move gravel or people if you're standing in the wrong place. This peak intensity, or sometimes the minimum intensity, is really what's going to be moving our electrons. So this is what we're often going to be caring about, and it gives us a good reference point. So the first and simplest measurement of a wave is simply the wavelength. So this is going to be the distance in between maximums of light in the same phase. So again, we're looking at the distance from in between maximums as it's traveling through space. You can also do the same things with minimums, but watch out to make sure that you don't try and accidentally do maximum to minimum, because that's a good way to get a half a wavelength instead of a full wavelength. Similarly, we often like using our maximums or minimums, and be very cautious when using your nodes, because one full wavelength isn't from one node to the next. It's actually going to be for two nodes, going from here past this one to here, because that gives me the full wave behavior. So this is one full wavelength. This is one full wavelength. This is half a wavelength, because I got halfway to my full oscillation. Now, the other major number we use is frequency. So this essentially is going to be telling us how many waves are going to strike a single point in a given amount of time. So again, this can be imagined like standing in the surf. Simply how many times are you getting hit by that peak intensity? And we typically are going to be using measurements in a number of waves in a given second. However, one of the reasons why we like to do this is because this also is the same units as hertz. So if you see hertz, that is a per second measurement. So if you see me use hertz, that's really what I'm talking about. The last one is really a chemistry special, and this is wave numbers. So wave numbers essentially comes from a historical little oddity. That it turned out one of the best ways to actually try and measure a wavelength originally was you'd go ahead, you'd set your light to shine into a crystal, and then it would go ahead and split your light. And you'd be able to essentially see how many peaks show up in a given in a given distance. And that's really what wave numbers are, is it's how many waves are going to be present in a single centimeter. So you can imagine if you were able to shine this on the correct behavior, you could simply count 1, 2, 3, 4 as it essentially interacts with my light absorbing species. So this was, again, very popular traditionally for ease of measurement. However, it turns out that it does have a certain amount of mathematical convenience. As those who had PChem 1 last semester saw, it's often a very easy way to talk about the energy of given molecular movements. So because of that, it's tended to stick around. Now, well, you may have a kind of intrinsic idea in terms of wavelengths. One of the biggest things that we need to know how to do is how to convert in between wavelengths, frequencies, and wave numbers, because it turns out that each of these kind of has its own power in a given situation. So let's go ahead and start with, again, our idea of a single wavelength. This is one full oscillation of my wave as it's traveling through space. So we can imagine our wave moving from left to right at a given speed, specifically the speed of light. So now I need to try and figure out how to convert this wavelength, which I can measure, into frequency. So what we can do here is we can make use of some classical physics, and that we can get our frequency by knowing how fast the wave is moving and essentially how far it has to travel. Now, it turns out light always moves at the same speed of about 3 times 10 to the 8th meters per second. So this is essentially equivalent to about 300 megameters, or about 300,000 kilometers per second. So this is a very fast sort of movement. Now we can turn this into wave numbers, into frequency, by taking that speed of light and then dividing it by our wavelength. And then this gives me my frequency. However, another kind of easy way to look out of it, and perhaps the way that's the easiest for me to think about it, is wavelength is a distance and frequency is per second. So the number, the amount of waves passing every second. So this is a distance per second. Well, distance per second is the same as speed. So simply multiplying these two values by each other should give me the speed of light. And this gives me an easy way to either go from wavelength to frequency or frequency to wavelength as needed. Now, converting to wave numbers is a little bit trickier. But if we think about it as the idea of wave numbers as number of waves present per unit distance, what we can do is simply say that if I say have a wavelength of 1 centimeter, this means I should have a wave number of 1 wave per centimeter. And it turns out that this tracks as about wave numbers being the inverse of wavelength. The smaller the wave, the more waves I can keep into a single distance. And again, typically, we're going to be trying to do this conversion with our wavelengths in centimeters. However, occasionally you will find wave numbers present in other units, such as per meter or per nanometer. But again, typically, we'll see per centimeter, again, for those historical reasons. However, one of the reasons why wave numbers typically sits around is because when we try and convert it from, instead of being with reference to wavelength in terms of frequency, what we find is by inputting our frequency, our equation of wavelength for frequency in, what we find is that wave numbers and frequency are proportional values. They essentially differ by the speed of light. And as we're going to see, what we end up typically having is most light has very high frequencies, but reasonably decent wave numbers. So if I want to use a property that is frequency dependent, but is a little bit numerically easier to work with, that's really where wave numbers shine. Not to mention, for a lot of, again, those historical reasons, most of our instrumentation tends to report everything in terms of wave numbers. Not to mention, one of the things you have to be aware of is that our book is written by spectroscopists, which means that they love themselves some wave numbers. So your book is going to almost be exclusively working in terms of wave numbers. Me, as a more quantum mechanics guy and with a more physics education, I'm a big fan of wavelength. So don't be too surprised if you have a lot of problems where you need to convert in between these two, as me and the book are in disagreement. However, this is also, again, a very frequent problem as you're working in between different disciplines. So one of the big things that we need to try and do is kind of get an instinct for how all of these kind of interrelate. So a good place to start is looking at our good old friend, the electromagnetic spectrum. So good place to start is keeping in mind that visible light typically goes from about 420. So this is going to be our violet light, up to about 700 nanometers. So this is going to be red. So if you have a wavelength that is smaller, which is going to be higher energy, that's going to be our ultraviolet. If you have a wavelength that is longer, so lower energy, this is going to be infrared and eventually down to microwave. So we're going to be mostly working in 3 general regions: visible and ultraviolet, infrared, and microwave. So Microwave, one of the reasons why microwaves are so important is because what they do is they take electromagnetic radiation, so essentially very uh, high wavelength light, and use that to excite water molecules. So essentially, what they do is they cause our water molecules to rotate, and that rotation imparts energy to the water molecules, thus heating them up. However, we can also use microwave spectrum to tell us a lot about the rotations of other types of molecules. So our microwave spectrum is kind of centered around wavelengths of about 1 centimeter. So you can convert this into frequencies of about 30 gigahertz. So that would be 30 times 10 to the ninth hertz. So again, very fast frequencies. And again, this is that beautiful point where our wavelength and our wave numbers are identical. Because if I have a wavelength of 1 centimeter, that means I have one wave in a centimeter distance. So again, you get lucky occasionally. The next up is infrared radiation, which most of you are familiar with from organic chemistry. So this is where a lot of our bond vibrations occur. So if you're looking at, say, infrared spectroscopy, very typical sort of wavelength is 5 micrometers. So you can then convert this into frequency, which gives us a frequency of about 60 terahertz. So yep, we're into high frequency light. That would be 60 times 10 to the 12th hertz. You start to see the reason why we're not huge fans of using frequency. However, wave numbers gives us a nice simple wave number, about 2,000 inverse centimeters. So those of you who kind of need a refresher, that would be, say, an alkyne stretch. So again, kind of in the middle of the spectra, not somewhere in between, say, CH and good old CC bond stretching. Then our last region is, again, the visible. So let's take green light. It's sitting kind of right in the middle, 550 nanometers. Well, this ends up being about 545 terahertz. So again, still very large frequencies. But you'll notice that this is the point at which wave numbers aren't quite so useful, as we now have about 18,000 wave numbers. So typically, spectroscopists dealing with wave numbers are often going to be focusing in on the infrared and microwave, where wave numbers are very convenient. Wavelength is also tends to be the most convenient when we're sitting going from near infrared to ultraviolet, but is also still fairly useful all the way into the X-ray, where you're down to, say, a single nanometer. Frequency turns out to actually be very important, because frequency, as we're going to see later, is really what relates to a lot of energy properties. And really, it's physical chemistry, so we're here for the energy. So next time, we're going to be taking our basic understanding of light and applying it to one of the big fundamental questions of early physics. What the heck is a black body? Till then, take care.